Chapter 10 is all about comparing two groups. So whether that means comparing two populations or comparing two different treatment groups from an experiment, either way it's about comparing two groups. Okay? So what we're going to do is we're going to use all the information that we've learned so far to talk about the inference and predictions and estimations that we can make off of samples from two groups that we then can compare. Okay, the foundation for that is the sampling distribution. So specifically, we're going to talk about proportions first and then means, like has been our tradition. So what is meant by the sampling distribution of the difference between two proportions? Okay, what that means is that sampling distribution is all the possible values of p hat sub 1 minus p hat sub 2. Okay? P hat sub 1 is the sampling proportion from one population, and p hat sub 2 is a sample proportion from another population. And so then I subtract them to get the difference. And how often these values occur. Okay, there is a caveat. The caveat is that p hat 1 and p hat 2 must come from two independent random samples. Okay? Independent in this case does not mean that each observation has to be independent, even though they do. Independent in this case means the samples have to be independent of one another. So I can't take like a sample from a population, keep it, and then take another sample from the population without allowing those original values from the first sample to still be eligible. Okay? That's going to change my probabilities of what I could get the second time for the second sample, and therefore make it not independent. So they have to be two independent random samples. So since we're talking about the sampling distribution of the difference between two proportions, let's talk about the shape, center, and spread of that distribution, because you're going to need to know the shape, center, and spread, or information about it, in order to correctly do our inference procedures. So, the shape, center, and spread of the sampling distribution of p hat 1 minus p hat 2. First, I want to make sure we understand what p hat 1 and p hat 2 are. Okay, so let's say that we have this sampling distribution. And it is full of p hat 1s. Okay, this means I've taken some population. Okay, that's a 1. Some population, which we're going to call P1, and I've taken all the different possible samples that I could take out of P1, and from each of those samples, I calculated the proportion of successes. Okay, that's a p hat. When I graph all those p hats together, okay, all those p hats from population 1 together, I get the sampling distribution. Some things to know about the sampling distribution. Shape. Okay, it's normal if, okay, and this is a rule that we already know, the sample size of this population, or from this population, times the population proportion, it's got to be greater than or equal to 10. And likewise, the sample size from this population times 1 minus the population proportion also has to be greater than or equal to 10. Okay, the center the mean of sampling distribution of p hat 1 is just whatever the population proportion is. Okay, remember, we should remember that from chapter 7. Our mean is equal to our population proportion. And then for spread, our standard deviation of p hat from this first population would be P sub 1 times 1 minus P sub 1 over N sub 1. Okay, remember that this has a condition that has to be met. The 10% condition must apply for me to be able to talk about the standard deviation of the sampling distribution, meaning my sample size can be no more than 10% of my population. Okay, so that's P1. Now let's look at another one. Let's say we have a second population that we're going to call P2, and from it I take all the possible samples that I could take, and from each one of those samples I calculate a sample proportion. Okay, and I graph all those sample proportions together, and that's the sampling distribution of P hat from the population 2. Okay, it's also going to be normal if the sample size from this population times the population proportion is greater than or equal to 10. And the sample size times 1 minus that population proportion also has to be greater than or equal to 10. Okay, the center, so the mean of P hat sub 2 is equal to just the population proportion for that one. And the standard deviation of P hat sub 2 is equal to the square root of P sub 2 times 1 minus P sub 2 over N sub 2. Okay, now let's say I wanted to combine those and subtract every one of these minus these. Okay, that's going to give me a brand new sampling distribution because I'm going to take all the possible values, okay, all the possible values of P hat 1 and P hat 2 and subtract them. And that's going to give me all these values of P hat 1 minus P hat 2. And how often they actually occur. And when I graph them all, I get the sampling distribution. Okay. If you remember from chapter 6, when we talked about combining random variables, the only way to know that this one is normal is if both the P1 and P2 were normal. So I have to go up here. For this one to be normal, it has to meet all 4 of these conditions. Okay? So this is normal if all the normal conditions, which are these 4, are met. Okay, hopefully you remember that when we talked about center, if I wanted to find the mean of 2 variables subtracted from one another, that's just the mean of each one of those subtracted. And since the mean of P hat 1 is just P1, and the mean of P hat 2 is just P2, that's how I find the mean. Okay, the spread is the one that people often goof. Okay, the spread one is a formula that y'all have known for a while. If I want to find the standard deviation of P hat 1 minus P hat 2, I take the standard deviations, okay, so that would be these right here, square them. By squaring them, I really just get rid of the square root. So it would be P sub 1 times 1 minus P sub 1 over N sub 1 plus P sub 2 times 1 minus P sub 2 over N sub 2. Okay, like I just said, I just square them, I add them together, and then I take the square root. And that gives me the standard deviation. And remember, 10% condition also must apply. Okay, so now that we've talked about the shape, the center, and the spread of the sampling distribution, let's talk about the standard deviation. I want to make sure we understand what standard deviation is. And the meaning of it doesn't change just because we're talking about sampling distributions. Basically, standard deviation tells us how far a data point is from the mean on average. Okay? That's what it tells us in the sampling distribution, except our data point and our mean have a couple different meanings. Our data point is the estimated difference. So basically this is telling us how far the estimated difference that we just calculated Okay, so that's the one we calculate based off of sample data. The standard deviation tells us how far that distance is from the true actual difference. So if I actually know the population parameters, what is the true difference? So standard deviation tells us how far apart those are. Remember, the true difference is also the mean. Okay, so it tells us how far the estimated difference is from the true difference, and then you got to remember our magic words, on average. Okay, remember all standard deviations tell us the same thing. They tell us on average how far away we are from the mean. So let's look at this example. So we're going to suppose that two counselors at school 1, Michelle and Julie, independently take a random sample of 100 students from their school. Okay, they're telling us here, this is keywords, independently take a random sample. That tells us the two samples they took, even though they're from the same population, are independent of one another and both random. So Michelle and Julie could have sampled the same students if they had come up during the random sample. If that wasn't the case, then they wouldn't be independent. So they're recording the proportion of students who did their homework. Okay, when they're finished, they find that the difference in their proportions is 0.08. They're surprised to get a difference this big, considering that they were sampling from the same population. Okay, I'm going to tell you that the population proportion, okay, the P for their school is 0.7. Okay, so PM would be 0.7 and PJ would be 0.7 because they're both working from the same population. So if I'm going to describe the shape, center, and spread, to talk about the shape, I need to check my conditions. So, N times P for both populations. So, 100 times 0.7, that equals 70, which is greater than or equal to 10. And 100 times 0.3 equals 30, which is also greater than or equal to 10. Okay, that's meant for the first one. Because they're from the same population, the P's are the same and the sample size is the same. So I need to say over here somewhere, condition is the same for both populations. Okay, so then I find the mean, P hat M minus P hat J. And to get that, I would subtract the two proportions. Well, 0.7 minus 0.7 is 0. So my mean is 0. So then I do the standard deviation. I need to say that I can assume that there are more than 1,000 students in this school. Okay, so then that would be 0.7 times 0.3 over 100 plus the same thing because it's the same population. Then take the square root. And whatever I got there, that would be my standard deviation. And tell me how far away, okay, this 0.08 is on average from, or how far the estimated difference, ours is 0.08, is on average from the true distance. True difference. Okay, so let's find the probability of getting two proportions that are at least 0.08 apart. Okay, look at this wording. At least 0.08 apart. What that tells us is that it doesn't matter which one's bigger. It doesn't matter if I'm doing P hat M minus P hat J or P hat J minus P hat M. Okay, I'm looking for at least 0.08. So 0.08 in either direction. So if my mean is 0, I'm looking for 0.08 or larger, or negative 0.08 or smaller. Okay, I know this is normal, so I can use normal CDF. I want to find my z-score. 0.08 minus 0 over, and then I need to know my standard deviation, plus 0.7 times 0.3 over 100. That gives me a z-score. And I can just type in normal CDF, okay, from 0.08 to some really large number. 0 is my mean. This right here goes in my standard deviation. Okay, that's going to give me a value for this area. Then to make sure I get both areas, I need to take this and I need to multiply it by 2. That's going to give me my probability of getting two proportions that are at least 0.08 apart. Okay, and when I do that, I actually get .2184. So no, the counselor should not have been surprised to get a difference that big, because this probability is almost like 22%. So it is too big for them to be surprised. 0.08, a difference of 0.08 totally could have happened by chance, or it could have been the actual proportion.